Hello, thanks for clicking, and welcome to another Unarculus production. Today, we are going to talk about a couple of items. We're going to talk about composite functions, and actually, we're going to be talking about the limit of composite functions. Okay, composite functions you learned back in Algebra 2. And we're also going to be talking about our first theorem in the course called the squeeze theorem. All right, theorems are something that you learned probably and used all the time back in shapes class, geometry. Remember that one? It was the one that had the shapes in it. But in AP Calc, we tend to use theorems a lot. They're featured on the exam all the time. And what we do is we look at them a little bit more in depth than maybe you did in geometry. All right, and they're the way you use them in geometry. We use them a little bit more in depth here in the calculus. Okay, so the first thing we're going to do actually is we are going to talk about the limit of composite functions, but let's first take an example, something that you did before. We'll stay on this title page here momentarily, and let's remember an example that maybe you did, let's say back in Algebra 2. So here's two functions, f and g. All right, so let's say I were to ask you, so a composite function is this, f of g of x. Right, that's a composite function. And let's say I were to ask you to calculate f of g of 2. All right, so to calculate f of g of 2, the first thing that you do is you'd look inside first, right? You do what's in the parentheses. So you calculate g of 2, and g of 2 comes out to be 2 cubed, or 8. So then that means you want to calculate f of 8. Well, f of 8 is just 8 squared, which is 64. Okay, so that's what you did like in Algebra 2. So what I want you to take from this is the fact that what we did is we looked inside first, calculated this value, and then worked with the value we got to calculate the outer function. Okay, so that's really what I need you to take from this for now about composite functions. But now let's go talk about the limit of composite functions. Here we go. So the limit of composite functions. Now, there's all this information here, and we're going to talk about this information momentarily, but let's look at it, okay, from similar to the example that we just did, right? So let's actually start with the conclusion that we make. The conclusion that we make says the limit as x goes to c of f of g of x, you can calculate it by first finding the limit as x goes to c of g of x. That's the inside function. That's exactly what we did a minute ago. Okay, and then, so there's a step here that's kind of missing, but it is very important. Sometimes it needs to be there and sometimes it doesn't. So we're definitely going to include it because sometimes it needs to be there. So for example, let's come back up here and it says let f and g be functions with the following limits. The limit as x goes to c of g of x is equal to L. So this limit came out to be, was equal to L. All right. Now, what you are actually doing is, and they tell you the conclusion is you find f of L. And sometimes that is true. You can do that. But what you really should be doing after you do this first step is you are actually going to calculate the limit as x goes to L of f of x. That's what you're actually calculating. Okay? Because if you think about it, think about our example that we did a moment ago, right? We had g was equal to x cubed, and then f was equal to x squared, and we calculated g of f of 2. Oops. So g of f of, oh no, we calculated f of g of 2. I know I could have erased that, but the eraser's all the way down there. F of g of 2. So g of 2, we did that first. We got 8, right? And then after we got 8 for this, we calculated f of 8. So really what's happening is 8 is now the x value. Well, in our case, we're talking about limits. So the x value is what you're actually approaching, right? So I'm approaching L, okay? So x approaches L of f of x. The question is, what do you get? All right, so that's really what you're doing here, okay? And then in some cases, you do in fact get f of l. All right. So let's go on, and we'll see a couple of examples of this so that you kind of get the idea. One of them's easier, and one of them's a little bit more complicated. So let's take a look at this. I want you to calculate for me the limit as x goes to 0 of f of h of x. All right, so to do this, okay, the first thing you're going to do is you're going to calculate the limit as x goes to 0 of h of x. That's the first thing we're going to do. Limit as x goes to 0 of h of x. All right, so let's go on h of x. Here we are. We're on h of x. Limit as x goes to 0. That means from the left and from the right, you got to go to the same place. From the left, from the right, I go to 0. I don't care that it's an open circle, right? I don't have to stand there. I just have to walk toward it. That's what we've already learned. So from the left and from the right, it goes to 0. Okay, now I know this value is 0. So what I'm going to do here is I'm going to take the limit now as x, and again, it happens to be 0 again. So as x goes to 0, but that 0 is actually from here. It's not this 0. It's the 0 that we got as a result of f of x. All right, of f of x. So the limit as x goes to 0 of f of x. As you go to 0 from the left and from the right, you go to -1. So that means the limit as x goes to 0 of f of h of x is in fact -1. And that is the correct answer. Okay, you're all done. All right, it's that simple. Okay, all right, so let's look at one that's definitely more complicated. All right, here we go. So this one, I'm going to compose something with itself. All right, so this is f of x, and it's the only function that I actually need because I'm using f of x twice in the problem. All right. So what I want you to do is I want you to calculate for me the limit as x goes to 0 of f of x. All right, so the first thing you're going to do is you're going to go inside and you're going to calculate the limit as x goes to 0 of f of x. We're talking about the inner f. Okay, that's this one. All right, so now the limit as x goes to 0 of f of x. Okay, so go to my graph of f. From the left and from the right, it goes to 2. So now I'm going to calculate then the limit as x goes to 2 of, again, now I'm going to do the outer f of x. All right, now let's see this. From the left, I go to 0. From the right, I go to 1. So then the limit as x goes to 2 of f, that limit doesn't exist. So the first thing I'm sure that you would write is you would think, well, this limit doesn't exist. I'm going to write dne. But that is actually wrong. That is not the correct answer, and there is a reason for it. Okay, so let's look a little bit closer at that first limit that we calculated. The limit as x goes to 0 of f of x came out to be 2. All right? But if you look at the way we approached the y value of 2, take a look from both sides, from both the left and from the right. We approach 2 from underneath it, right? So what do I mean from underneath it? So if I'm on the number line here, okay, from underneath 2 means I'm getting closer to 2 from the left-hand side of it, right? Because on a number line, I'm approaching 2 by looking at numbers like 1.9, 1.99, right? 1.999 from both the left and from the right. Those are the numbers I went through to get to 2. So I'm actually finding the limit as x goes to 0 of f of x, the inner function, it is 2, but it's approaching 2 from the left. Okay? So this is really one of the only circumstances you would need to even consider that. All right, but you are approaching 2 from the left, which means that now, if I want to do this second limit, I'm actually approaching 2 from the left-hand side of f of x. So go back to f of x and approach 2 only from the left. And if you do, you get 0. So the limit as x goes to 0 of f of x is 0. That is the correct answer. Okay, so it's not as simple sometimes as just, calculate two limits, an inside limit and an outside limit. Sometimes you do have to do a little bit more thinking about that inside limit that will help you determine that outside limit. All right? All right, so there's a little bit more complicated example. Okay, so now let's go on, and we are going to talk about our first theorem in this course called the squeeze theorem. Okay, so you can read it here. It says if f is less than or equal to g, which is less than or equal to h, so I have three functions where x is near a, except possibly at a. And I also know a couple other things. The limit as x goes to a of f of x and the limit as x goes to a of h of x are both equal to L. Then I can say for certain that the limit as x goes to a of g of x must be L. And whether you know that or not or recognize it, when we look at it, you'll definitely be able to tell me that that has to be true. It's got to be true. Okay, so let's see what this is all about. So in this class, like I said, theorems are very important to us, and we need to be able to analyze them and understand them, not just be able to use them in examples, all right, which is kind of what you did or really worked with like in geometry, right, back in shapes class. You said, just tell me what the theorem is that I can use it, right? Just tell me what the theorem is so that I can use it and set the two equations equal to each other so I can solve for x. All right, but here it's definitely a little bit more different, more difficult and a little bit more different. All right, so first thing that we have from geometry, back from shapes class, is we have a conditional statement. Okay, if then is a conditional statement. If all of this that's written here is true, if all of this is true, then I can make this one little conclusion. All right, so to show that the theorem actually works, what we're going to do is we are safe to assume that all of the stuff in the if part of the statement is in fact true. All right, so let's draw a picture because that's going to make things way easier when we see exactly what it is we are looking at. All right, so let's make a picture. Okay. Let's talk about our three different functions. Let's start with f of x. So we have a function called f of x. F of x, the only thing I know about f of x is I know for certain it is the smallest of three functions. It could also be equal to these. All right. Okay, so it has the smallest y values. And I also know the limit as x goes to a of f of x is equal to L. I can assume that. All right, so let me put a down here, and I'm going to put L here. Okay, so I know that the limit as x goes to a must equal L. All right, so let me try to draw that here. There we go. I think we have it. There we go. So there's my function f. I'm just drawing anything as long as when x goes to a, the y value goes to L. There we go. We have it. Okay. All right. Now, g of x, I know something about g of x, but we're going to come back to g of x in a second. Let's go on to h of x. Take a look at h of x. I also know some things about h of x. I know h of x is bigger than f of x, right? Its y values are larger, so it's going to be higher. It's going to be up here, okay? And I also know the limit as x goes to a of h of x is also L. Well, that's convenient. Okay, so let me draw h. I'm going to draw h up here. But remember, I also have to draw it so that its limit happens to be, as x goes to a, happens to be L. There we go. There's h. All right. Okay, so now I have f of x and I have h of x. Okay. So now let's go for g of x. So the only thing I really know about g of x, based on the information that's been provided, is that g of x is between f and h. Okay. It's bigger than f of x or equal to it, and it's smaller than or equal to h of x. So g of x must be somewhere in the middle here between my green graph h and my red graph f. So I'm going to draw g of x. It's got to be stuck in between. Okay, all right, so let me draw it. There we go. Okay. All right, there's g. So now there's my picture, and here's the conclusion. Then, if you draw all of this correctly, if all of this is true, and based on what we drew, it's all true, then this must be my conclusion. The limit as x goes to a of g of x must equal L. So let's take a look at that picture. Well, as x goes to a of g of x, yeah, it equals L. And that should make sense to you because f of x went to L, h of x went to L, and g of x is in between them. So there's no place else that g of x could possibly go other than L. Hence why we call this the squeeze theorem. Okay, we've squeezed g of x between f and h. Some textbooks also call it the sandwich theorem. Okay, right? Sandwich theorem for obvious reasons. H and F are your bread, and then G is your peanut butter, right? So you got bread, peanut butter. Okay, so the peanut butter is stuck in the middle. All right, that's your G of X. That is the squeeze theorem. That's our first theorem. Okay, again, what you need to take from this is that all of this stuff, we had to say all of this stuff was true. Then, as a result, this was the conclusion that we made. Okay? All right, so now let's see how the squeeze theorem works in practice. Okay, it's a little bit tricky. All right, let's try a limit. Let's try to calculate the limit as x goes to 0 of x squared sine of 1 over x. So the first thing you'd always try to do when you do limits is you could separate these limits, right? We could write the limit as x goes to 0 of x squared times the limit as x goes to 0 of sine 1 over x. Okay, so we could separate them. All right, so the limit as x goes to 0 of x squared would just be 0. The limit as x goes to 0 of sine of 1 over x, sine of 1 over 0, that's undefined. Sine of undefined, I have no idea what this is. So this to me looks like it's some kind of limit that doesn't exist. That would be my guess just by looking at it. So the question is, what is 0 times dne? 0 times dne is no idea. Okay? It's not a determined limit. It's not considered indeterminate like we talked about with 0 over 0. It's just a limit that you cannot calculate. All right? So the question is, how do you calculate then this limit? So what we're going to do is we're going to use the squeeze theorem. So now we have to think about what the squeeze theorem says. The squeeze theorem said that a bunch of things had to be true, right? So the first thing that had to be true is the major part of it is that you have to have three functions to work with: f, g, and h. And you have to have one of them stuck in between two others. All right, so what we're going to do is we're going to look at this limit here. And I actually do see something that I recognize that is in fact stuck between two other things. Okay, and that I see right off the bat. All right, it's not exactly what's there, and we'll talk about that in a minute, is this. The sine of x is between -1 and 1, always, right? Okay, there's your unit circle, right? Here's your unit circle, remember it? Unit circle, here's 1, -1. Okay, sine is the y coordinate, right? And if you're on the unit circle, you ain't going above 1, you ain't going below -1. So it is true that sine of x is stuck between -1 and 1. Now that kind of looks like this that we have up here, right? Three functions. G of x is stuck in between two other functions. Sine of x is stuck in between 1 and -1. Okay, now we need to figure out how to get this in the game, right? We really need an x squared sine 1 over x in the game. And where do we need it to be? We need it to be in there, in the middle. All right, so I'm going to take a step here. I'm going to claim the following must also be true. The sine of 1 over x must also be between -1 and 1. Okay? I claim that is in fact true. All right, you're going to provide for me an explanation as to why you think that is true. Okay? You don't have to get it right, but you do have to provide for me an explanation as to why you think it's true. And we'll talk about it. Okay? Now, that's good, but I don't have the x squared. So, well, what I could do is I could just multiply this by x, put an x squared here, but I can't just randomly put one there. I'd have to put one there. I'd have to put one there, there, and there. Okay, I'd have to put one in all 3 spots. So that is legal. It's an inequality. I multiplied them all by the same thing. So now, what do I want to do? I want to calculate the limit of all 3 of these. Here we go. Oh, let me erase this here. Unit circle. And the limit as x goes to 0, whoops, 0x. Okay, and I am hoping, if I find the limit of all, at least the 2 on the outside, based on the squeeze theorem, I'm hoping that these 2 limits are the same, right? So the limit as x goes to 0 of negative x squared, well, that's just 0, 0 squared. So that's less than or equal to the middle limit, which is less than or equal to the limit as x goes to 0 of x squared is also 0. So this limit is stuck in between this value and this value. It's stuck in between 0 and 0. Well, then the limit as x goes to 0 of x squared sine 1 over x must be 0 by the squeeze theorem. Okay? Must be 0 by the squeeze theorem. That's the only thing that could possibly be true. It has to be 0. It has no choice. There's nowhere else for it to go, right? There's nowhere else for this middle limit to go. Okay? So there's an example of you using the squeeze theorem. All right, now, not all of them are going to be this difficult, but I can give you some hints. The squeeze theorem, okay, is a nice thing that you can occasionally use. Sine and cosine functions are great for the squeeze theorem if you're really in trouble, right? If you're in some kind of wacky scenario like this, okay, the squeeze theorem is definitely something you might want to look at, especially if there's a sine or a cosine function inside here. Okay, that's really a good time to look for it. All right. Some people ask about tangent. Tangent, no way. No way you'd use the squeeze theorem with the tangent, because if you remember what the graph of tangent looks like, it looks like a cubic. And it is not bounded. It's unbounded. Okay? The reason sine and cosine work so well is because they're bounded on the unit circle, right? So bounded means they have an upper bound and a lower bound. That's the mathematical definition of bounded. All right, upper bound and lower bound. So sine and cosine are nice examples of places where you might need the squeeze theorem at some point. But again, you always check the limit first, see what you get. But if you get some disaster like this, yeah, the squeeze theorem may in fact come into play. Okay? All right, that's it for the first day. Okay, I hope you enjoyed the video. And as always, thanks for clicking.